Okay, for this video, we'll be starting with general wave properties, but it is part 2, so it is sound. Okay, used to be that sound is a separate chapter, but due to the change in syllabus, they put it everything under waves because sound, I'm sure you have heard of sound waves, right? So for this part of the lesson, we'll be talking more about longitudinal waves. Okay, I hope you still remember what longitudinal means and what you have to think of when you hear this word longitudinal. Okay, so let's start. We continue with success criteria F. Okay, so it shows an understanding that sound can be produced by vibrating sources and a medium is required for the transmission of sound. That means I must have a source that vibrates so that it can produce sound. Okay, and basically sound is a kind of energy and we need a medium to transmit the sound. Okay, so waves can transfer energy without transferring metal. So for this, you have actually learned in the first part of waves, right? Energy can be transferred, but the metal is not transferred. Okay, what is being transferred is energy. Okay, sound is a longitudinal wave. This is important. So longitudinal, you think of this word called, you think of parallel. Yes? Okay, so sound is a longitudinal wave traveling in the air, but it can also be in other medium like water, okay, and maybe those solid as well. So this is the sound is produced by a vibrating source. That means the source, there must be some vibration to it. I need energy to make the source vibrate. So this is important. Basically, this is the definition of longitudinal waves. They are waves that travel parallel to the direction of the medium's particle vibration. Medium can either be solid, liquid, or gas. Okay, so let's say now I'm talking. The medium is actually air. I made the air particles vibrate. So let's say I made it vibrate going left to right. So this is the particles vibration. Okay, the sound wave will be in the same direction, parallel to the direction of vibration of the medium's particle. So this is opposite from transverse. Okay, this is different from transverse. Remember transverse? Okay, something like that. The particles actually go up and down, but the waves go in a direction that is perpendicular to it. Okay, so this is the particles vibration, but the wave direction is perpendicular. So the keyword to think of is perpendicular for transverse waves. Okay, so production of sound is produced by vibrating sources placed in a medium. So it can either be solid, liquid, or gas. The medium is usually air, but it can be any gas, liquid, or solid. And sound relies on the passing on of motion from a group of particles to another through collision. So they must touch each other. Okay, and that is why sound cannot travel through a vacuum. In a vacuum, there are no particles, right? So even though energy, I may cause something to vibrate. Example, let's say inside I have and this is a gas jar. Okay, inside is vacuum. Okay, I may make this thing vibrate. I knock on this gas jar, but because inside is vacuum, there are no particles. They cannot help to transfer the energy through collision. So this is one very important difference between sound waves and other kind of transverse wave. So this is what is happening. I may show you a video in class. Now when the air is removed from the bell jar, the sound of the bell becomes softer and softer until we cannot hear it. Okay, so maybe in the video we can see that the striker is actually still striking the bell. So by right there should be some sound that we can hear. But as the air is being pumped out, so it creates a vacuum. So there's no particle inside to help with the transmission of sound. Okay, so for pure students, you may not have this in your notes. Okay, so this is you may want to add in. Sound travels at different speeds in different medium. In general, the speed of sound in solid is faster than the speed of sound in liquid, and it is the slowest in gas. Okay, so do you know why? Okay, so this one you can actually explain using kinetic model of particles. In solid, particles are closely packed. Okay, particles are closely packed and in fixed position. Right? So if I make a group of particles in the solid, one end of the solid, I make the particles vibrate. Okay, so let's say example, this group over here, I made it vibrate. Okay, so the other particles, the solid particles which are nearby, will also be set into vibration, right? Because they are closely packed and they are in fixed position. However, for gas, remember the particles are in random motion, they are moving around and they are very far from each other. So it's very difficult for me to make one particle to pass on the energy through collision to another particle. Okay, so it will be slower, right? So therefore, speed of sound in solid is faster than liquid, faster than gas. You have to use a kinetic model of particles, the arrangement of the particles to explain. Okay, so let's look at question F1. A speaker is placed next to a lighted match. A loud sound wave is played through the speaker, causing the flame to vibrate. Okay, basically it's the air around the speaker that vibrates. Now, which type of sound is emitted from the speaker and in which direction does the flame vibrate? Okay, so the wave type is longitudinal because the speaker emits sound wave. Okay, and the direction of vibration will be in this direction, parallel to it, because if the sound wave is coming out this way, the direction of vibration of the wave of the air particles will be in a direction that is parallel. Okay, so answer is B. Okay, next, which rule about light waves and sound waves is correct? You haven't really learned about light waves, but light waves, you know, it is transverse. Okay, it's a transverse waves. Sound, it is longitudinal. Okay, so in our syllabus, the only example for longitudinal wave is sound wave. Okay, so for light wave, it can actually travel in a vacuum. Okay, because light wave is just pure energy that is being emitted from the sun. Okay, but sound wave, they actually need a medium, so they cannot travel in a vacuum. So answer is B. Okay, so you must be sensitive to all these keywords. When you see vacuum, you must think of certain concepts that are linked to it. Okay, let's go to success criteria G. Describe the longitudinal nature of sound wave in terms of the processes of compression and rarefaction. Now, this compression and rarefaction is only for sound waves. Okay, so when you see in a question it mentions compression and rarefaction, you know you are doing a chapter on sound. Okay, so propagation of sound wave, that means it's the movement of sound wave. It's just a very another word to replace motion or transmission of sound waves. Okay, so like all longitudinal waves, sound waves propagate as a series of compression and rarefaction. So these are keywords that you need to put in when they're asking for explanation answers on what are sound waves. Okay, so very important keyword, compression and rarefaction. Now, compression is a region where the air particles are closer together. So if it's happening in liquid, then you must say where the liquid particles are closer together. Okay, you get the idea, just adapt and change. So it results in an air pressure higher than normal atmospheric pressure. So this is compression. But rarefaction is a region where particles are far apart, result in an air pressure that is lower than normal atmospheric pressure. So you can see from this diagram here, at 1 we actually have a tuning fork. Okay, and all these are actually just models to show the arrangement of air particles, okay, that are not moving. Okay, so the layers of air are in undisturbed position. Now when the prongs push outward, so when I hit the prong, it will vibrate. So when it push outwards, a region of compression is produced. So over here. Okay, so I will push the original layer here towards the second layer. Okay, so this is my compression. And when this air layer of particles, they collide, right, they will bounce back. they will bounce back. So it results in a region of rarefaction. But this energy of pushing and pulling will result in a series of compression and rarefaction. So as long as the prong is continuously vibrating, is continuously pushing and pulling the air particles around it, I will then have a series of compression and rarefaction. Okay, so if I'm able to, like, let's say, map out the particles, right, I will have compression where the particles are close together, air pressure is higher. I will have beside it a layer of rarefaction, okay, where the particles are far away and lower than atmospheric pressure. Okay, so as the sound goes from left to right, the particles also vibrate in a direction that is parallel to it, also in a left to right direction. Okay, same direction. Okay, so now we go to graph. We have pressure distance graph. So this is something like your DD graph, right? You look at the x-axis, it is distance along the hollow pipe, and this is air pressure. Now, still remember, for air pressure that is high, it is actually compression. Air pressure that is low, it is rarefaction. Okay, so you see that if I'm charting the air pressure, so if I have very high air pressure, that is going to be my compression, right? All of these are compression. Then all of these are low pressure, these are rarefactions. Okay, so I'll just put a letter here, C, 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 to show compression, R, R, and R. So this is how I can convert a longitudinal wave to look something like a transverse wave. Okay, and what does it mean? So from compression to compression, okay, the horizontal distance is actually what we can get called the wavelength. Okay, because sound is a kind of wave, so we also have wavelength. So compression to compression is wavelength. How about rarefaction and rarefaction? Because assuming that the compression and rarefaction occurs at the same frequency, okay, so I'm going to have the distance between rarefaction and rarefaction to be a wavelength. Okay, so we can also get amplitude from the y-axis. It is the maximum pressure change. Okay, we are using the y-axis. What's more important is the x-axis is in terms of distance, therefore it is the wavelength. How do we get wavelength? It is from compression to compression or rarefaction to rarefaction. Okay, so this is nothing new. You learn this in transverse wave, DD graph, right? Wavelength. So this is why I said just now, assuming that the sound is continuously produced, the rising and falling of air pressure is regular and continuous. Okay, we can also do a DD graph. Okay, just now was pressure and distance. Now we go to DD graph. Now let's understand this part of the diagram first. So all these are the air particles at the undisturbed position. Okay, all these are the air particles at the undisturbed position. Now, then a wave comes along in this direction, from left to right. Okay, so at this particular time instance, okay, we see that, wait, before that, I need you to annotate all this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, and 16. So you see that we have 16 position. So at 16, all 16 position, they each have a air particle example. Okay, and they are equally spaced. Okay, because this is just a model. So you see that at position 1 for the next graph, this is my first particle. Right, you see that it has shifted from position 1 towards the right. We have particle 2, particle 3, 4, 5, 6, particle 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Okay, so this is important because I'm going to tell you which particle is remaining at its position. So particle 4. Can you see that? It is at, comparing it to the original, it is at its original position. That means it didn't move. Who else didn't move? If we go down the line, we see that particle 10 as well. Yes. Then who else? We see particle 16. Okay. So you see from 4 to 10 is about a difference of 6. From 10 to 16 is also a difference of 6. Okay, so you must be thinking, really man, the particles really line up so nicely? Of course, this is a model. We just use this as a model to teach this part. Okay, so we see that particle 4, 10 and 16 doesn't move. Okay, let's look at particle 4. For particle 4, do you see if the particles beside it are moving towards him or away? Okay, it is actually towards. Okay, who is moving towards particle 4? Particle 3 from the left to the right, moving to 4. Particle 5 moving from right to left towards particle 4. So you see that particle 4 is facing 2 particles going near it. And even particle 2, 6 and 7 and 1, they are also moving towards particle 4. So particle 4 is actually a center of compression. You see that? It is where the other particles, 1, 2, 3 from left to right, 5, 6, 7 from right to left, moving towards particle 4. So it is a center of compression. Okay? How about particle 10? Particle 10 did not move as well, right? Okay, then can you look at particle 9 and 11? Are they moving towards or away? They are actually moving away from particle 10. Particle 9 is going from right to left. Particle 11 is going from left to right. They are moving away from particle 10. Therefore, particle 10 is the center of rarefaction. Okay, so this is how we identify the compression and rarefaction. Of course, they stop at particle 16, but if you just look at particle 16 is also not moving. Then we can deduce from particle 15, who is moving from left to right towards particle 16, that 16 is going to be the center of compression, right? It's going to be alternating between compression, rarefaction, and compression again. Okay, so if it's compression, right, the displacement, remember particle 4 doesn't move, so the displacement is going to be 0. Similarly for particle 10. Okay, and then particle 16. Okay, so this is where we map out particle 4, 10 and 16 on the x-axis. Then how do we get this transverse or sine looking wave? Okay, so now I need you to look at particle 1, 2 and 3 because particle 4 doesn't move. Particle 1, 2 and 3, which particle actually moved the most? It's actually particle 1. So if I see particle 1's original distance and where particle 1 has shifted to, this is the amount that is being displaced. Okay, so this is amount or the distance that particle 1 was displaced. If you look at particle 2, did it move as much as 1? No, it's lesser. Particle 3 is lesser than 2 and definitely lesser than 1. Particle 4 did not move at all. So I can safely say that particle 1 has the maximum displacement and that will give me its amplitude. Okay, particle 2, if you map out, is only a small distance. So this is where particle 2 will be. Okay, this is how much is displaced. Particle 3 is like that. So this is particle 1, this is particle 2's displacement, this is particle 3 displacement. So with that, we can actually map out. So particle 5 is also move a certain distance, but because we choose going to the right as positive, so particle 5 will be at the negative displacement. Does it make sense? Okay, then we map out particle 6. Okay, it actually moved a greater distance than particle 5. Okay, particle 7 actually moved the most. So it's going to be in a negative displacement, right, in the negative direction. Therefore, it's going to be the lowest point. Okay, so there you have it. We have our crest and trough again. So remember, for DD graph in transverse wave, crest to crest actually gives me the wavelength. Okay, crest to crest actually gives me the wavelength. And because particle 1 moved the most, and who else moved the most? Particle 13 as well, in a positive direction. So crest to crest in a DD graph will actually give me the wavelength. Okay, this will actually correspond to the distance between particle 4 and 16, right? Because they are both compression. Okay, however, because they are in the they are not displaced, but we know that particle 4 and 16, they are crest to crest. Particle 4 and 16, I say again, they are compression to compression, so that will give me the wavelength as well. And if you measure, it should be the same as what we have drawn up here. Okay, so this is how we map sound wave, which is doing compression and rarefaction, to get what we have as a DD graph, a displacement distance graph. Okay, so in exam, they can either give you pressure distance graph, take note of the x-axis, distance. They can also either give you a displacement distance graph. So just bear in mind, what can we get from PD or DD graph? It is the wavelength. Okay, sometimes they may ask you for the amplitude as well. That's where you need to see which particle actually moved the greatest. And you will actually have to map them out. Okay, mark out particle 1, 2, 3 from their undisturbed position, and then you see which particle actually moved the most. Okay, so just take note of note 1 and 2. Okay, so let us compare a DD graph and PD graph, displacement distance, okay, and pressure distance. Okay, so there's a subtle difference. So this is compression, right? For a displacement distance, okay, so this is compression, this is rarefaction. So I have compression again, and then rarefaction again. Okay, but when it's translated to a pressure distance graph, compression is actually maximum pressure, max pressure. Rarefaction is minimum pressure. So this is the comparison between displacement distance graph and pressure distance graph. Okay, so compression to compression, we can actually get wavelength, right? Compression and compression. So this is my compression, this is my compression, I can get my wavelength. Either case, you can always fall back on how do we get a complete wave, right? To get a complete wave, okay, then that is in the horizontal distance, that is going to be my wavelength. Okay, so we have a DD graph, displacement distance, and pressure distance graph. Now we go to displacement time graph. For displacement time graph is actually a video of a particle. Okay, video of one single particle. So at time t equals to 0, this particle is here. Okay, at t equals to t over 4, that means 1 out of 4 step, the first step, the particle is going to the right. Okay, can you see here? Then 1 step later, so this is 1 step, 2 steps later, it went back to its original, but that is not a complete wave yet, right? It needs to go in the opposite direction to the maximum negative displacement in 1 more step, and then finally for the 4th step, it arrives back in the original position. And that is where we get our motion of each particle. Okay, so now if I were to map out, if originally I'm here, you will go to the right, come back, and if you turn it around, it will look at like your DT graph. Okay, the maximum distance that it moves will then be the displacement. So this is 1 step later, 1 step. Okay, then it goes back to original undisturbed position, 2nd step. Then it goes in the opposite direction, 3rd step, and then finally it goes back to its original position. So we have 4 steps, 1, 2, 3, 4. So what can we get from a DT graph? Remember, we can get period, yes, from the x-axis. And what else? We can also get amplitude, okay, from the y-axis, which is the maximum displacement that it experiences. Okay, so note 1, displacement time graph is drawn for a single particle. So we need to sort of assign the positive and negative direction. Okay, right may be positive, left is negative, up to you, you can choose. Now the speed of the graph is given by the gradient. So the gradient changes, the speed of the particle is not constant. The speed is maximum at equilibrium position. Where's the equilibrium position? Here, maximum speed, and 0 at amplitude, right? Because it has already reached the maximum position, so the speed is 0. The speed is 0 speed. Okay, so this is nothing new. You have learned it before. Okay, let's try. G1, the graph shows at one instant, okay, the pressure variation along a sound wave. So let's look at the axis of the graph. It is a pressure distance graph. That means from the x-axis, we can get actually the wavelength. This is pressure, so we can then determine maximum pressure is compression. Minimum, the lowest pressure is rarefaction. So this is P is going to be my compression and Q is going to be my rarefaction. This is also be my compression. So compression to compression, that means X is the wavelength. Yeah. The Y then will be the amplitude. Okay, if we can actually later on translate it to the maximum distance. So Y is actually the change in pressure, if I were to put it. Okay, but of course Y is then used in our options as a distractor. So where is the rarefaction? They're asking for rarefaction. Rarefaction will be at Q. Okay, so answer is C. Can? Okay, G2, a sound wave travels through air as a series of compression and rarefaction. Right, so these are the keywords. Which role compares the air pressure in the compression and rarefaction to atmospheric pressure? This is easy. Air pressure in compression will be higher. Air pressure in rarefaction will be lower. So answer is B. Simple. Okay, so I think I'll stop here for success criteria F and G. Okay, I'll continue in the next video.